Recall the idea that we experienced with the depth function, that if we have a quantity f of x, let's say we have a depth that's represented by big F of x, and we take its derivative, we're going to get the rate at which the depth changes. And we might represent that by little f of x. Of course, that's big F prime of x. Little f of x is big F prime of x. But if we consider this to be the rate, then we know that by integrating the rate, we get the change in the quantity f of x. The integral doesn't exactly give us the function f of x, it gives us the change of f of x. But if we then know an initial value for the function, we've got the function from the change. So we can essentially get the function back by integrating its derivative. Again, if this is a depth function and this is a rate of depth change, and by integrating the rate of depth change, we can find the depth change between any 2 points. And we make the statement that we can integrate the rate to get the change in the quantity. Integrate the rate of depth change to get the change in depth. Integrate the rate of temperature change to get the change in temperature. Integrate the rate of change of money to get the change in the amount of money. Specifically, what we get is when we integrate a rate between two values of x or t, depending on what our function is, we get the change in that quantity, where little f of x is the rate, and big F of x represents the amount of the quantity that we have. Again, in our first model, if big F represents the depth, then we have the depth at time b minus the depth at time a. That's the change in depth between time a and time b. Integrating the rate function, the rate of depth change, again, that's equivalent to finding the area under the rate graph. And that, as we know, also gives us the change in the quantity. This statement more or less constitutes the fundamental theorem of calculus. We have another picture down here representing the rate situation for a depth function. The graph is not particularly well drawn, and we're not going to get it to line up very well. But if we have a rate in centimeters per second and a clock time in seconds, then a typical trapezoid under the graph has an area which is equal to the average altitude, which is the average rate, multiplied by the width, which is the time interval. The area then equals the average rate multiplied by the time interval. The rate is in centimeters per second, the time interval is in seconds, and when we multiply an average rate in centimeters per second by a time interval in seconds, we get a change, a delta, in the depth. Okay, change in depth. And this is essentially saying the same thing that this integral is up here, because this integral simply represents the sum of all the areas under all the trapezoids. In a limit, of course, as the width of the trapezoids approaches 0.